So we're going to continue on in Chapter 4, where we're talking about naming molecules, specifically hydrocarbons, both acyclic and cyclic. We're going to talk today about rotation around sigma bonds and why that matters. We're going to talk about why certain bonds have free rotation and other ones don't. We're going to talk about Newman projections, which is a way of representing so-called conformations, or things that occur because of rotation around a single bond. And then we're going to talk a little bit about conformational analysis. And this is something that you're going to have to be able to do in terms of determining more or less how the energy changes when we rotate around a carbon-carbon single bond, for example. Okay? So this is where we ended off last time. We didn't quite get to the nomenclature of cycloalkanes. We know that from last time we have a few things that all names have, right? They're going to have a prefix, a parent, and a suffix. What does the prefix tell us? The substituents and where they are, right? What does the parent tell us? Longest chain. And the suffix? The functional groups, right? So the only difference between cycloalkanes and alkanes is this other term that we add, cyclo, okay? So the first thing that you're going to do is find the parent cycloalkane. In this particular case, we got 6 carbons in the ring, so it's a cyclohexane parent, okay? And we have 2 alkyl groups on it, right? What are the 2 alkyl groups here? We have an ethyl and a methyl group, that's right. And so we're going to have to figure out how to number so that we know where our ethyl and our methyl groups are located, right? If you have a single substituent on the ring, you need not number it. You do not need to say 1-methyl cyclohexane, because no matter which carbon you put that methyl group on, it's always going to be number 1, okay? Not necessary. So here we have methyl cyclohexane. Here we have cyclopentane, but this group that's attached to it is known as tert-butyl. How do we come up with the name of tert-butyl? It would be from, it's a butane parent. We've seen that we have 4 carbons. And yeah, this would be a tertiary carbon if it was not an alkyl group, right? It would have a hydrogen on it. Removing that hydrogen from that tertiary carbon is how we come up with tert-butyl. But the easy way to remember it is it looks like a T. Okay? So tert-butyl. Okay? Tert-butyl is one of those substituents that doesn't really follow the IUPAC nomenclature rules, but it's, or systematic rules, I should say. It is an IUPAC accepted name. So if we look at dimethyl cyclohexane that we see here, you can see that we can number either in a clockwise fashion or in a counterclockwise fashion. Why is it that numbering in the clockwise fashion here is the correct way to do it? The lowest possible number, that's right. So we start at 1, 2, 3. So we have 1,3-dimethyl cyclohexane. If we numbered in this direction, we would have 1,5-dimethyl cyclohexane. So this is kind of going with that first point of difference rule, right? And so here we would have the correct numbering system. So we would number in a clockwise fashion in this particular case, okay? Now, if we have 2 different substituents, in this case we have ethyl and methyl, okay, we are going to we're going to give the lowest number to the substituents alphabetically, right? Ethyl, E comes before M in the alphabet, right? So it's going to take on number 1. And so we can either number 1 going this way, or we can number 1 going this way. And in this case, we have a 1,3. If we do the other way, we would have a 1,5, and so 1,3 is clearly how we want to go. So this is 1-ethyl-3-methyl cyclohexane, right? We would not number 1 being the methyl group. Now, one of the things that people do that gets confusing here is they forget about the alphabetical part. And they'll go, oh, well, there's 2 carbons up here. That should take priority over a single carbon. That's not how it works. The rule is based on the alphabet, okay? So now, there is a situation where you can imagine having an alkane that has both a long chain and a ring. Then we have to make a decision about what's going to take priority as the parent. If the number of carbons in the ring is greater than or equal to the number of carbons in the longest chain, the compound is going to be named as a cycloalkane. If that is not the case, it's going to be named as a cycloalkyl substituted alkane. Okay, and we'll see an example here. So if we look at this particular case, we notice that we have 6 carbons in the ring, but our alkyl group only has 1, 2, 3, 4 carbons. Okay, so we're going to name this as an alkyl substituted cyclohexane. So here we have butyl cyclohexane. Why no numbers? Only one substituent, right. So cyclohexane is the parent, butyl is the substituent, and we have butyl cyclohexane. If we look at this particular example, we see that in the ring we have 4 carbons in the ring, and we have 6 carbons in the chain. So here we're not going to name it as a cycloalkane. We're going to name it as a cyclobutyl substituted hexane. So we've got 6 carbons in the longest chain. We circle that. That becomes the parent. And at carbon number 1, we have a cyclobutane group minus a hydrogen, so it's cyclobutyl. And now we have 1 cyclobutyl hexane. Here we had to number, correct? And why? That's right, because we could imagine this cyclobutyl being on carbon number 2 or carbon number 3, right? And so it does matter the numbering here, okay? So this is the correct answer. This is a alkyl or a cycloalkyl substituted alkane. This is an alkyl substituted cycloalkane. So being able to count up to 10 or so is kind of important here, all right? There are some other common names that you need to commit to memory, and these common names come from their shapes, okay? And everybody always finds this cute, okay? So, real easy. That looks like a cube, right? That is cubane. This kind of looks like a house. It is houseane. This kind of looks like a church with a steeple, right? It is known as churchane. And this kind of looks like your Easter basket, right? It's called basketane, okay? Kind of commit them to memory. Cubane is kind of interesting. Can anybody tell me what's interesting about cubane? Well, what's interesting about it from a chemist's point of view? What kind of hybridization should those carbons have? sp2? Are there any double bonds? They should be sp3, right? Everything's singly bound. But what about the bond angles? They're 90 degrees. So what would you think about cubane? Stable or unstable? It's fairly unstable. And in fact, it's very energetic. And in fact, the military spent a lot of money at one point trying to figure out how to make nitro derivatives of cubane for explosives. Cubanes have been studied for that kind of thing because you have a lot of ring strain, as we call it, within the molecule. And so they wanted to exploit that ring strain for practical purposes. Okay, so, but nonetheless, cubane does exist. You can make it, you can put it in a bottle, but it also will catch fire quite easily and do a number of other things. Okay, so we have cubane, houseane, churchane, and basketane. They are all hydrocarbons. Okay, but nonetheless, I would dare say these are not things that you could derive based on the IUPAC nomenclature rules. Okay? Bicyclic compounds. These are compounds that have more than one ring. Okay? So for example, this molecule, it has more than one ring. How many rings do we have? Why do we have 2? Let's build a model, see if we got 2. Let me snap together the right number here. It's the same model kit you got.
Well, I want the neat organized thing. I can't ever find the ones I need.
Okay, so I'm going to put these together. So I've got 3 carbons there, put in a 4th, put in a 5th, put in a 6th. Together. And that's what I've got. If you look at the projection, you'll see that that's the same thing, right? So you can see how that's projecting onto the screen, minus my hand. Okay? Now, if I look at this, I can imagine a ring being something where I start at one point and never lift my finger and get back to the starting point, right? Would you all agree that that's kind of a ring? So you can imagine that there's 1, 2, 3 rings. But the answer would be wrong. There are only 2 rings in here. This is a bicyclic compound. The number of rings is equal to the number of disconnections that you have to do to get it completely open. So if there's 1, there's 2. It is a bicyclic compound. So the number of rings is equal to the number of disconnections that you have to make from your model kit. Okay, so this is a bicyclic compound. Okay. Now, if we look at this molecule again, you'll see these carbons that are in red are known as bridgeheads. They're what connect the 2 rings together, basically. Okay? So we have a 2-carbon bridge here in blue. We have another 2-carbon bridge here in blue. And then we have a single carbon bridge there kind of in pepto-bismol. All right? So you'll see a bicyclic compound actually has 3 bridges. This is the bridgehead. This is the bridgehead. So I can go from bridgehead to bridgehead this way. I can go from bridgehead to bridgehead this way. Or I can go from bridgehead to bridgehead this way. Okay? So we have 3 different bridges. 2 bridgehead carbons, if you will. Okay? And so we can draw it flat like that, although it's actually a 3-dimensional model. Okay? Now, naming it is determined by first counting the total number of carbons in the bicyclic ring. How many total carbons do I have here?
7.
I've got 7. So what's it going to be? It's going to be a heptane parent. That's right. Okay? And so if we look at this model, we see that we've got 7. So it's going to be a bicycloheptane of some sort. We have to know how the bridges are. Okay? And so we note that we have a 1-carbon bridge and 2 2-carbon bridges. So the name becomes bicyclo 2.2.1 heptane. Bicyclo because I've got 2 rings. I've got a 2-carbon bridge, a 2-carbon bridge, and a 1-carbon bridge. That's what these numbers tell us. Okay, so I've got 7 carbons in a bicyclic system, 2, 2, 1. And it always goes largest to smallest. Not the other way around. That would be incorrect. You go from the largest to the next largest, so on and so forth. In this case, 2, 2 happen to be identical. Okay? Does that make sense? So once we have a bicyclic compound in our hands, we need to figure that out. Okay? So before we build a model, let's do an example. Name that compound for me. How many carbons do I have? I've got 6, 7, 8, 9, 10. Decane, right? Okay. Where are my bridgeheads? Okay, so what are the numbers in my bridges? How many carbons do I have in this bridge? 4. How many carbons do I have in this bridge? How many carbons do I have in this bridge? 0. Well, you don't count the bridgeheads. Right? If you add up these numbers, the numbers will always be 2 less than the total number of carbons. Because you don't count the bridgeheads. So I have 4, 4, and there's nothing there. 0. Okay? 440. So bicyclo 440 decane. What did I do with my? Here we go. So let's build a model of an alkane and an alkene. Get your model kits. And let's build butane, which is 4 carbons long. And let's build an alkene. So let's build trans 2-butene. So you got to have the 2 sp2 pieces, and then you've got to have a double bond piece. That's how that works. Snap them together. You might have to get rough with it. Trans 2-butene. Butane. How is trans 2-butene and butane related? Are they isomers? There are 4 carbons in both. What's the difference? Yeah. This one is 2 hydrogens less than this, right? So it's a unit of unsaturation, right? Now, take your trans 2-butene molecule and try to rotate around that carbon-carbon double bond. So what can I rotate around in the 2-butene? I can rotate around the sigma bonds, right? How about with butane? I can rotate around everything, right? And so this actually has a fairly fixed conformation. This one, I could look at it like this, I could look at it like that, or like that, or like that, right? I got several different conformations that I can look at. So we have free rotation around the carbon-carbon single bonds, but we do not have free rotation around the carbon-carbon double bonds, right? All right. Now, if we look at the alkane, what we'll note is that we can rotate around the sigma bond. Will you all agree that the molecule here on the left is different than the molecule on the right? Why is it different? Aren't they all connected the same? I haven't changed the connectivity. Why are they different? Pardon? One of them. The carbons are in the same position, basically. It was rotated, right? So if I look at this red sphere and this white sphere, for example, they're about 180 degrees from one another. But here, they're more like a cis conformation to one another, right? Even though we don't have cis and trans in alkanes, okay? So the location of the atom changed upon rotation. Are they equivalent? They are not the equivalent in terms of energy, okay? You will have a scenario where one of these actually is lower in energy than the other, and this is what we call a conformational analysis, which you all will get very, very good at by the time you leave this class, okay? Now, drawing things like this can become quite painful. But there is an easy way to draw these things, and it's called a Newman projection. Okay? And so if we take, for example, just 2 carbons, just to make it simple. A Newman projection is what I would see if I could project a 3-dimensional structure looking down a bond onto a 2-dimensional surface. That's exactly what I'm doing right now. I'm using the light from the projector to project down this bond onto that surface. Okay? We have to have a way in which we can represent this, though, accurately on a 2-dimensional piece of paper. So looking down this carbon-carbon bond, I'm going to have a back carbon and I'm going to have a front carbon. The back carbon is represented as a big circle by definition, and the front carbon is represented by a dot. What is attached to that back carbon? I've got 3 hydrogens, and how are they? One's coming up, just like that, right? Notice the line from the hydrogen to the carbon stops at the big circle. What's attached to the front circle, or front dot? 3 carbons going, or 3 hydrogens going how? Notice the hydrogen from the, or the bond from the hydrogen to the carbon looks like it goes across that big circle. That does not mean that it is bound there. This is a projection. So if I imagine, wish I could hold it a little better. See if we can do that. That's the Newman projection, okay? And you can actually build a big model, go outside on a nice bright sunny day at noon and make nice Newman projections on the sidewalk, okay? The bright light will give you these Newman projections, okay? So when we are looking at a Newman projection, basically what we are doing is grabbing the bond that we are looking down and we are orienting it such that we can look down that bond, just like that, okay? And so this is my front carbon, that would be the dot. That's my back carbon, that would be the big circle, and I can see exactly what's attached to it. We do not draw the bond between the 2 carbons because I can't see it in the Newman projection. I'm looking down it, okay? All I can see are the 2 nuclei, or actually the front nucleus, okay? So this works really well for carbon-carbon single bonds, okay? And so you're going to draw in the bonds and then draw in what's attached to it. Now, if we look at butane, here we have a series of carbon-carbon single bonds that we're looking at, or conformations that we're looking at. Which bond are we looking down? There's a lot of carbon-carbon single bonds. Which carbon-carbon single bond are we looking down in butane? What is that, though? What number? 2,3. We're looking down the carbon-2, carbon-3 bond. Anytime somebody says you need to look at a Newman projection, they need to indicate which bond that is. I've got carbon-1, carbon-2, carbon-3, carbon-4, right? And if I turn it like this, that's the first Newman projection that I'm looking at. Let me turn it right. Correct. There's my back carbon with my methyl group sticking up, the 2 hydrogens out to the side. Here's my front carbon with the 2 hydrogens up here, and the methyl group going down. I am looking down the carbon-2, carbon-3 bond. Okay? Now notice we can rotate an infinite number of degrees, right? I mean, you can divide a circle by infinity. But we typically look at these as 60-degree rotations. So what carbon is actually being rotated here? And which one's holding steady? The back carbon is being rotated, right? So I have this to start with, okay? Which is called the staggered anti. Where do we come up with that name? Okay, very good. And why do we call it anti? They being what? Okay, so these methyl groups are 180 degrees to one another looking at that Newman projection. That is the anti-conformation. Now I'm holding the back carbon here and the front carbon, and you say I'm going to rotate the back carbon, right? By 60 degrees. And so that's the next Newman projection. That is an eclipsed Newman projection. Right? Because if I look down that carbon-carbon bond, I see that the hydrogens are eclipsing each other. This methyl group and this hydrogen are eclipsing each other. This hydrogen and this methyl group are eclipsing each other. Notice they draw them just a little skewed so that you can see everything. Okay, but that is an eclipsed conformation. Now we rotate another 60 degrees, and we're going to put this methyl group in between this hydrogen and this methyl group. Okay? You can see that. This is, again, another staggered conformation, but it's called gauche. Okay? Now we can rotate another 60 degrees, and we end up with, let's see, where are we? Here we are. And we end up now with another eclipsed. Is this eclipsed the equivalent of this eclipsed? Why not? All right, so now the methyl groups are actually eclipsing each other. They weren't doing that up here, right? It was just methyls and hydrogens that were eclipsing each other. So this is called the methyl-methyl eclipsed. I can rotate another 60 degrees and I go back to another staggered gouge. I can rotate again and I end up at another eclipsed, and then I rotate another 60 and I'm back at my starting point. Okay? Does that make sense? Okay. Let's do a little demonstration. All right. This is my software package that I was telling you about that costs $1,200 again. Okay? So you've got this model kit, which does pretty good showing me the different conformations, right? And so what I have here is actually butane, and how would you have it oriented to match what I've got up there? Methyl, methyl eclipse, that's right. So basically that's what I've got. You can see how it overlays, right? In the projection there. So that's what I'm looking at. What's the angle? What's the dihedral angle between this carbon and this carbon? Got to go back to some of your trig. I'm talking about the angle of the projection from here to here. What's the dihedral angle? 0. This is a 0-degree dihedral angle. Okay? They are eclipsing one another. Okay? So these methyls are eclipsing one another, and we have a dihedral angle of 0. That's what's shown here. So really what my computer software is doing is plotting the relative energy of these different conformations versus the dihedral angle. And so I told the computer that every so many degrees, I forget how many, to rotate it and actually calculate what the new energy was. Okay? And so I made a movie out of it, and what you can see is we can rotate, and I'll turn that to where we actually have the Newman projection.
So it's a high energy like this.
No. Which one's higher?
I mean, there.
Nope. Look at the values. Those are negative values. Up there's positive. Huh? Well, no, not number-wise. Negative is less than positive, right? What? This axis? This is the dihedral angle. Okay, so here the dihedral angle is what? No, here. 180, right? So the dihedral angle from here to here is 180, and that's the lowest energy conformation. So now what's happening? As let's do this. Let's stop the movie. And let's go here at the lowest energy. Okay, so there we have the lowest energy. And we're going to rotate it just a little bit. So we'll go up to the next one. So as we're rotating this one, why is the energy going up? Are the methyls getting closer together? What's getting closer together? Notice that's the highest energy in this region right now, right? And what happens as we rotate just a little bit more? It dips down a little bit, right? So if the two methyls were getting closer, then it would still be going up, right? So what's happening from here to here? That's right. We're getting the methyl in the same space as the hydrogen. And what happens when you take two people and you put them in a really tight space? They're not very comfortable, are they? The same thing here. I've got this big methyl group and this little hydrogen, but they're starting to try to occupy the same space. Okay? And so the energy goes up. But that's not the highest point on the overall energy curve. Why? Why is that only? Because hydrogen's kind of small. So I've got a large, small interaction. As I start to rotate away from that, what's happening? It's going down again because we're not eclipsing anymore, right? And it will go down until we get to around what we call a relative minimum, which is what conformation? That is gauche, right? So it is staggered, and it is staggered gauche. So we have a hydrogen, we have a methyl group, and this methyl group is kind of in the projection in between both of them, right? Notice it's not as far down as the anti. Explain to me why the anti is lower in energy than the gauche. That's right. So I've got a big group and a big group. They're not eclipsing each other yet, but they're starting to get close, right? Here, what about it? They're as far apart as possible. That's as far as you can get them away. That's going to be the lowest energy conformation. Okay? So now what happens as we continue to rotate? It goes up, right? Until we get to the very top, which is where we have the methyl-methyl eclipse, right? So the methyl-methyl eclipse is going to be the highest energy conformation. And as I start to rotate again, what happens? It starts to go down until we get to here, which is a relative minimum, and then it starts to do what again? Go back up as we start to have a methyl hydrogen eclipse, and that's going to be a relative maximum, and then we're going to go down again to we're at the absolute minimum, right? Or the global minimum, as we like to call it in computational sciences.
Will the eclipse generally always have a higher energy level than the gouge?
Yes,
So
absolutely.
So that's like an actual thing.
Yeah, I'm taking these two large things and I'm trying to make them occupy the same side of the world, basically.
And the larger those are,
The bigger they are, the worse it gets. Yeah, so if I added, say, another couple methyl groups here, and let's say had isopropyl groups, the energy would actually be much larger. Okay? The overall profile would be about the same, but the energies would be different. Okay? So I don't really care that you memorize what these energy values actually are. Okay? But you will, I now tell you this, on an exam you will have to do this type of conformational analysis. Okay? It's very important that you be able to look at a graph like this and tell me what the various points are. What is that relative minimum? That's a gauge conformation, right? What's the absolute minimum or global minimum? It's the anti. What's the highest energy? Methyl-methyl eclipsed, right? So, you know, how would I do that on a multiple choice exam? I'd give you several different Newman projections. I would give you a graph, and I would ask you to place them where they need to be placed on the graph, okay? So you need to always read the graph very, very carefully, because if you look at how I've plotted it here and you look how your book's plotted it, it will look different, okay? It's because your book did not start at 0. They put 0 in the middle and then plus or minus 180 and plus 180, whereas my computer just plotted it from 0 to 360, okay? But it's the same thing. Always look at your axes and know what you're dealing with, okay? So a dihedral angle is always between about a bond, and it involves 4 atoms. In this case, it involves carbon 1, 2, 3, and 4, but it's the dihedral angle that results by rotation about carbon bond 2 and 3. It's the projection, right? If I look at that, if I look at the projection from here to here, right, it would look something like that in the projection on the ground. And that is a dihedral angle that results. Okay? It's about taking a 3-dimensional object and projecting it onto a 2-dimensional surface. Pretty much so like what you're doing. Yep. All right, we still got some time, so get your model kits. Let's build some more things. Where's mine? Oh, there it is. Build and name that. How many carbons do we have? 8. How many rings do we have? So what's the name? It is a bicyclooctane. What are the numbers going to be? What's in the middle? So build bicyclo 222 octane. You're going to need 8 carbons. Tell me something about some of the Newman projections. Look down some of the carbon-carbon single bonds. If you want to snap, you got to snap them together.
They're really hard to snap together.
They're real easy. Watch. Take your 2 pieces, put them like this, and then just pop. Don't try to push. Grab them like that and pop. There, close. And then make sure that they go on all the way. Yep. There you go. You got it. Mm-hmm. They are. Where are the bridgeheads? Nope. Where are the bridgeheads? What connects all the bridges together? There you go. Those are the bridgeheads. That's correct. Notice that the bridges, if I add those numbers, add up to 6, right? And it's always 2 less than the total number of carbons. Take your 2 pieces, put them together like that, pop.
Gosh, they're just stronger. I can't.
Nope, you'll be able to do it.
Oh, I got that one. It hurt though.
Pop. If you grab them and just try to force them like that with their legs, it won't work. You got to push on the C parts. No?
Oh, I got it.
Okay, you're struggling too much though.
It hurt.
Yeah. Put it like that. Grab like that.
Kind of like stretch it open.
Mm-hmm. How much free rotation does that molecule have? None? Not much. All right. Now take a 2-carbon bridge off. Just completely take a 2-carbon bridge off. Now you have cyclo what? Cyclohexane. How much free rotation do we have around cyclohexane? Ish? What's ish? It can wiggle. So if we build cyclohexane, find for me what you think would be the lowest energy form of cyclohexane and make an argument. There is no bridgehead at this point. My model kit's starting to really wear out. The bonds are. It turns out that this conformation is actually the lowest energy. If you take carbon 1 and carbon 4 and hold on to them, okay, it kind of makes what's known as a chair. Look at it, and it kind of looks like a beach chair, right? I've got the headrest, I've got the seat, and I've got the footrest. That is the lowest energy conformation. Tell me why. They are far apart. What else? What bond angles? In between the carbons? Pretty close to tetrahedral. What else? What if I grab it and I look down these two carbon-carbon bonds and do a double Newman projection? Huh? Nothing's eclipsed. Everything's staggered really nicely. What happens if I take the footrest and I fold it up and make it really close to the headrest? What do I look at when I see the Newman projections? Everything's eclipsed. So is this going to be more stable or less stable? Less stable. That's right. So chair is actually more stable than what we call boat. Notice it kind of looks like a little boat on the water, right? And in fact, we call these groups right here the flagpole hydrogens. Okay? So that's boat.
IUPAC thing? Or is that just like
Yeah. This is how we describe it.
I see a tent.
You see a tent? It is not tentane, nor is it botane. Okay? But we call that boat cyclohexane because it kind of looks like the bottom of the boat and then both ends. So, you don't see the boat?
I don't see a boat.
It's a boat.
Okay, picture yourself being a chemist in a lab for like 4 days straight, then you'll probably see a boat.
How would we name this molecule? Where do we get heptane?
Because there's 7 in the main chain.
Okay, so we got 1, 2, 3, 4, 5, 6, 7. So there's my main chain. How am I going to number it? From right to left or left to right? So I'm going to number 1, 2, 3, 4, 5, 6, 7. And why? The functional group? The substituent. How would I name the substituent? Not cyclopropane. Propyl, right? So how am I going to name it then? Pardon? It is a ring.
Isn't it like the least stable of the cyclos?
It is.
Because it has 60-degree angles between them, and that's not even close to 109.
Yeah, build a model of cyclopropane. Oh, you can. You actually have parts in your model kit to allow you to do this. So there are some pieces that are a little different color gray. They're kind of a metallic gray. They still say sp3, and they're a little more flexible. Use those for one of your carbons in a cyclopropane. And it keeps you from breaking the model. Looking at the model, what can you tell me about cyclopropane? It's not stable. I make cyclopropanes. That's what I did for my graduate work. Very easy to make. You can actually make them and store them quite easily. But what's weird about it? What if I look down the carbon-carbon bond and look at a Newman projection? Everything's eclipsed, right? What else do you notice? It's bulging. That's exactly right. What are the hybridizations on those carbons, as you all know hybridization? sp3. sp3 likes to have what kind of bond angles? 109.5. What's the bond angle in a 60 degrees? So this has what's known as a lot of ring strain. Notice when you open it up, you get a pop. That kind of gives you an idea of how much ring strain you have. It wants to open up, okay? And so these cyclopropyl groups are actually very, very important functional groups, it turns out if you ever use insecticides like Raid, the cyclopropane ring is one of the functional groups in most insecticides because it's highly reactive. Yep. Yep, you got it. Notice the bonds are bulging. So would you say that this is really and truly sp3 hybridized? Not really. It's more like sp5, which that gets kind of mind-blowing. You need the other piece. You need the mate to that. All right. Wednesday, we have an inverted lecture over the rest of Chapter 4, which is going to involve you looking at Newman projections down ring systems. So you need to look at all that before you come to class. Okay? Have a good day. Autumn, I have your exam.